Okay, so let's start the show. We were discussing essentially linear algebra, axioms of quantum mechanics. That's going to be the this is again continuation of the introduction for those not formally initiated in quantum mechanics. For those of you who know all these things, apologies. So, as we said, the state of the quantum system is described by a vector in the complex vector space. You just picked some bases and this guy, and essentially a complex inner product vector space is called a Hilbert space. Hilbert space, in a vector space, Hilbert space, which is essentially a complex inner product. So essentially it's a vector space with a well-defined inner product. Vector space. Essentially, if I have two vectors, I represent the inner product by in the bracket formalism as this thing. This is the bra part. This is the ket, the Dirac notation. And with this inner product, it means essentially I associate a complex number with two vectors. So associate a complex number with two vectors. I can also treat it as, let's say, what should I, let's say I treat it as this guy. So what does the symbol mean? This means that one can regard the inner product as a linear function from the kets to the complex numbers. So one can regard the bra, this guy, as a linear function from kets to the complex number space. Essentially what's happening is you have a linear function depending upon this phi, this row vector, which takes an input as all the kets, all the elements of your original vector space, and pops out a complex number. So that's another way of interpreting this inner product. And it's a linear function because if the input is a linear combinations of the vectors, this is just going to be translated into this guy. So Geometrically speaking, the inner product is a natural generalization of the dot product. One usually represents the ket space as column vectors, and the bra space as the complex conjugate transpose, the row vectors where each element is complex conjugated. So this would be your the bra space, and defining what's the advantage? Defining the bra space this way lets us define the norm or the length of the vector. See, ultimately, the whole point of physics is to, whatever your abstract formalism is, ultimately you need to calculate real numbers and map it to a real line, whether it's temperature, pressure, position, velocity. So all said and done, we are trying to formulate a theory of probability, and we took the route of linear algebra just to reconcile with the fact that uh, the state of the system, or let's say the state of the photon, can be in the upper mode or the lower mode of the beam splitter Mach Center setup. So to calculate the probabilities, we need the formalism of linear vector spaces, the bra space, the ket space. Just defining bra space this particular way lets us define the norm or the length of these vectors, because ultimately we are physicists, we'll be dealing with the lengths, so which is the norm of the vector, and defining the bra space this way lets us define the norm or length of the vectors. So you have the properties which you already know, linearity of the inner product, what else? By definition, the inner product when I change the role of two vectors, the inner product is the complex conjugate. It's anti-linear in the bra space. So, for example, anti-linear in phi. So, for example, if I have, let's say phi is a phi 1 plus b phi 2, then the inner product with another vector is antilinear. The coefficients come as complex conjugates. And of course, we already said. So either I'm going to represent the inner product by a bracket and two vectors, or I'm going to use my bracket formalism. So this greater than 0, that means basically that's by definition, that's the way I define the norm. And of course, this is equal only when the vector is 0. So two useful inequalities I would urge you guys to try and prove them yourself. Is the triangular inequality, which essentially is this guy. And also the Schwarz inequality. Just some useful things. So maybe as an exercise, please show them. So one can, for every vector space, one can define an orthonormal basis. And one can express any vector in that particular basis. This is the condition for orthonormality, that the inner product. I hope everyone's familiar with the Kronecker delta symbol. Okay, since it's an orthonormal basis, I have a useful identity. This is the identity operator. This is a very useful identity, and we'll be heavily using this identity. And as we discussed, if I have a vector, I have expressed it on an orthonormal basis, my coefficients are given by this guy, which is essentially, as we have discussed, the probability amplitude or the conditional probability amplitude. Well, it's easy to see. How do we get that? I express psi as, now what do? I stick in the identity. So for example, psi can also be written as psi j, ej. Remember, this is the identity. So what do I get? I call this particular quantity, well, so sorry, I screwed up the notation a bit. Let's say the basis vectors were ej, and let me call it psi. So I'm multiplying psi. I'm just packing up the identity operation over here, identity operator over here in this I, and now I can compare this with the coefficient to get Cj, each of the Cj as what I had demonstrated earlier. So the bottom line is this is a pretty useful identity. You tack it on anywhere and pops out the answers a lot of times. Okay, so well, for example, I have a vector j, and I have another vector. I express it in the basis set, and I need to calculate the inner product of these guys. What it essentially means is, well, the inner product you evaluate, it's going to come out to be this guy, or in other words, this is going to come out to be yeah. So essentially, how do I show that? Well, that is nothing but sum over j. What is dj star? Dj star from there, as we have already seen, is going to be this quantity, and cj star is going to be this particular quantity. And if you look at it, this is just the identity element. There is sum over the structure, which was the identity, that comes out to be this quantity. So you could have just started from this guy, inserted the identity over there, and then concluded the value of the inner product in terms of the expansion coefficients. Yeah, so we've already done with representation. I represent the ket as, I'll represent the another vector as d1, d2. Now, the bra corresponding to the ket over here is just the row vector complex conjugated. And this guy. And I can show the same thing by matrix multiplication over here. Okay, so in this bracket formalism, it's easy to see how linear operators behave. So I have a linear operator well, when by definition this is this guy, and I can either express it in this abstract notation as a linear operator, or I can have a matrix representation in terms of a basis, and where the matrix elements are going to be given by AJKs. So A representation, I have so on and so forth. So in other words, I have, let's say I have a linear operator operating on a vector in this Hilbert space. What do? I just tag along the identity again. So this is just to, all this is to make you guys familiar with this bracket notation, those who are not familiar, please try to do these elementary calculations yourself just to get a feel of the things. So what do I get? I tack along another identity over there. So I insert the identity at two places. And notice this quantity. This is the matrix element. So I get some sort of an outer product notation, what I call. I get sum over jk. I get an ej, ajk. This was ajk element. I get ek. That's going to be, since this is a number, I can get it over here. This is going to be ej, ek. So this is the representation of the matrix element on the jth row and the kth column. So that's going to be your ajk. And you can fill up the whole matrix through this. Similarly, the matrix multiplication, how does it look like? Well, again, I'll have to insert the identity a multiple number of times. Let me insert it over here, A. Then let me insert one identity between A and B. I'll use another index, B. And then I'll use another identity, L. So this turns out to be one matrix element, this turns out to be another matrix element, and this is the outer product. So I'll have JKL, I'll have essentially JKL, I'll have EJ, EL, that's essentially my matrix multiplication. And okay, so we already sort of introduced this notion of dual space. So I call a ket dual to a bra and vice versa. I have the ket space, which is a column vector, and I have a bra space, which is a row vector, which each element complex conjugated. Similarly, for an operator, let's say I hit this operator vector with this operator, this is going to result in a vector that's going to be dual of another vector which I represent by this symbol over here. We'll see a dagger, you can verify also, will be the complex conjugate transpose by construction. So essentially the idea is that you hit this vector by this, you get psi. Now the dual of psi would be the bra psi, and then you can ask what operator is going to give me bra psi, and the answer would be this guy over here. So this essentially means is that if I take a psi, I am trying to calculate the dual. What psi is going to be in the dual space, this is going to be represented by this guy. The A dagger is going to come out to be the complex conjugate transpose by construction. So yeah, we've already seen what happens to the vectors. This is all dual space. These guys. So the vectors over here are the column vectors, the vectors over here are the row vectors, and if I consider two vectors, let's come to the inner product. So consider two vectors. Two vectors. I represent the inner product as this guy. I can ask the following question. Let this inner product be let an inner product where an operator is applied to the second element of this inner product be equals to some operator applied to the first element. I can ask what is B. Well, B turns out to be a dagger, which I call it as a Hermitian conjugate or adjoint. Well, how do we show this? So it's rather not very hard. This is the inner product which I represented through, by definition, this guy is this thing in your bracket language, and I need an operator which is going to be yielding me the same inner product. So by definition, what I can do is that let me deal with the following way. So this inner product is equals to this inner product. Then what will happen is the following. This is just trivial mathematics. The goal over here is to just evaluate B. So what I did was this inner product, the complex conjugate of this inner product is this guy, which should be equals to this guy, the complex conjugate of this inner product. And now I can calculate B to be, well, let's see, let me work with some basis elements. Let's say I have, so this definition is valid for any phi and psi. So let me do it for basis vectors E1 and A2, an orthonormal basis. That's going to give me E1. Well, there you have. What do you have? So we already saw that this is how, these are the matrix representation in terms of an orthonormal basis. So this is going to tell me that the row becomes the column and the column becomes the row. They get swapped and the element also gets swapped. That's essentially what I mean when I call B equals to A dagger, which is actually Hermitian conjugate or complex conjugate transpose. So the matrix becomes a complex conjugate transpose I represented by B equals to A dagger. Yeah, so that essentially it. In terms of outer products, it's rather easy to see in terms of the bracket notation. You have a guy, this is an operator, mind you, this is an outer product. Mind you, this was a number, this was a complex number where a row was getting multiplied to a column. This is an outer product where a column is getting multiplied by a row. I'll get a matrix. So this guy daggered is going to turn out to be the roles of Brian get swapped. Nothing too profound about it, but that's just the way it is. So in other words, one more way to see is this: see the representation of A in terms of the matrix elements was jth row, kth column, and the matrix element AJK. A dagger was once again row and column swapped, and this guy becomes the complex entity over here. So this is exactly equivalent to what we are saying over there. Or in other words, I can change, since K and J, there is nothing special about K and J. This essentially means EJ, EK over here, and I just play with the indexes over here, EKJ. So essentially, it's all equivalent, just the matrix representations of the Hermitian conjugate operator. So the other properties of the Hermitian conjugate transpose or the adjoint operator is that it's antilinear. So if I have adjoint operation is antilinear. This gives me this guy. So now if I have the notion of the inner product, and let's say I am, by definition, that was the definition of my adjoint operation, I might as well regard this as this guy over here. So in other words, I can apply either psi taking the inner product with a psi, or I can call it an A dagger acting on the first element and then take the inner product. So one can apply the operator either from the left or from the right over here. So from the left and then evaluate this guy, or from the right side and then take the inner product with psi. So lastly, we come to projection operators. We've already seen projection operators when we briefly discussed measurements. So projection operators, essentially, let's consider this one-dimensional projection operators. By projection means I am projecting the vector in a particular subspace, whether it's a one-dimensional subspace or a two-dimensional subspace. But let's say the one-dimensional projector would be given by this matrix. Remember, it's outer product, this is the matrix. If it is orthonormal, then I have the norm to be 1. But essentially the idea is the following. I have a vector phi, and I want to project it in this particular direction over here. So what do? I'll project it using the projection operator. That's going to give me once again, I get a number, so I can write them down as I just take the number over here. So I projected phi by applying this projector to the vector, and what do I get? I get an amplitude. How much of psi is there in phi? How much of this component is in this particular vector along this direction over here? And of course, this, as you can see, is from the triangles rule, is going to be the original vector minus the projected vector. It's going to be this guy. We can have similarly multi-dimensional projectors. Well, I mean, let's say, let S be a d-dimensional subspace spanned by orthonormal vectors. The projection operator onto S is essentially the sum of all the 1D projectors. This structure is going to project any vector on this particular subspace. And this is going to be a unit operator in that particular subspace. Subspace S. But this is the way I define or generalize the notion of projectors to d-dimensional space. And as we've already seen, we are dealing with measurements which intimately involve projection operators. You know, remember we did this polarization where we were able to project the incoming light beam in some polarization into one specific polarization direction. So in the next lecture, we are just going to do some properties of linear algebra that are going to be useful for us for quantum information. So see you next time.